Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. I will discuss theorems on groups from the algebra of MSc post and semester post. There is theorem, let G be a group for any non-empty subset S of G. N of S is a normal subgroup of G. Further, for any subgroup of H of G, N of H is the largest subgroup of G in which H is normal. If K is a subgroup of N of H, then H is a normal subgroup of KH. Now, for proof, N of S is equal to X belongs to G such that X inverse is equal to S. As S E inverse is equal to S, we get E belongs to N of S. Let XY belongs to N of S. X inverse Y into S into X inverse Y inverse is equal to X inverse Y into Y S into Y inverse X. Therefore, S inverse X inverse into Y S Y inverse X X inverse Sx is equal to S. This shows that X inverse Y belongs to N of S, where Xy belongs to N of S. Therefore, N of S is a subgroup of G. Let H be a subgroup of G. Therefore, H is a subset of N of H, and H into H inverse is equal to H for any H belongs to H. Let H is normal subgroup of K, where K is any subgroup of G, then K inverse is equal to H for any K belongs to H. Hence, K is a subset of N of H. Now, for any G belongs to N of H, we get G inverse is equal to H. This shows that H is normal subgroup of N of H, and if H is normal in K for some K is a subgroup of G, then K is a subset of N of H. Hence, N of H is the largest subgroup of G in which H is normal. So next, K is a normal subgroup. K is a subgroup of N of H. Hence, for any K belongs to K, K inverse is equal to H, and hence HK is equal to KH. This shows that HK is a subgroup of G. H is normal in N of H, and K is a subgroup of N of H. HK is a normal subgroup of N of H. Therefore, H is normal subgroup of N of H. Therefore, H is normal subgroup of KH, as H is subgroup of KH. There is one more theorem. G is a subgroup and H is a subgroup of G, such that index of G over H is equal to 2. Then H is a normal. Then prove that H is a normal subgroup of G. We have to prove that GH is equal to GH. Select any G belongs to G such that G does not belongs to H. Therefore, G is equal to H union HG, and H intersection HG is equal to pi. Therefore, G is equal to H union GH, and H intersection GH is equal to pi. Hence, this is possible if and only if GH is equal to GH. Then others, for any G does not belongs to H, we get HG is equal to GH. But as for any H belongs to H, we have HH is equal to HH. For any, it follows that HG is equal to GH for each G belongs to G. Therefore, H is normal subgroup of G. Let there is one more theorem. Let G be a subgroup, G be a group, then the following statement are true. The state of conjugate class of G is a partition of G. Coordinate of class of G, conjugate class of G A is equal to index of G over n of A. If G is finite, then coordinate of G is equal to summation of coordinate index of G over n of A, where A is running over exactly one element from each conjugate class. Define a relation equivalence on G by A equivalence B if and only if B is equal to X inverse. This is an equivalence relation and relation on G, and the equivalence class containing A is C of A. Hence, G is equal to union of C of A, disjoint union. Hence, C of A such that A belongs to G forms a partition of G. To prove that coordinate of C of A is equal to index of G over n of A, let R denote the set of all right coset of n of A in AG. Define a map F from C of A to R by F of G inverse is equal to n of A G. F is well defined, obviously true. F is 1 that is nx is equal to nay. Therefore, xy inverse belongs to n of A. Xy inverse into A, xy inverse of inverse is equal to A. Therefore, xy inverse A is equal to axy inverse. Therefore, y inverse A y is equal to x inverse A x. Therefore, f of x inverse Ax is equal to f of y inverse Ay. Therefore, x inverse Ax is equal to y inverse Ay. Therefore, f is 1. Now, way to prove that f is onto, let NAG belongs to R. Then, for this, G belongs to G inverse AG belongs to C of A. Therefore, f of G inverse AG is equal to NA of G. This shows that f is onto. Therefore, f is onto, f is well defined, f is 1 homomorphism. Therefore, there exists a mapping f from C of A to R, which is both 1 and onto. Hence, C of A, coordinate of C of A is equal to coordinate of R is equal to index of G over n of A. Let G be a finite. G is equal to union of C of A over A disjoint union. We get coordinate of C is equal to summation of coordinate of C of A over A is equal to summation of index of G over n of A over A, where A runs over exactly one element from each conjugate class, and this is our main task.